This is a lightning frequency map, and really what this shows is a number of lightning strikes per region over a given period of time. And this can be used to sort of estimate the probability of experiencing a lightning event in any particular portion or region of the globe. What I'd like to point out is if you look at South America, or especially Florida, this has a very high concentration of lightning events. So the likelihood of experiencing a lightning event in these areas is much higher than it would be, say, in the European region or in the Pacific Northwest. So the chances of experiencing lightning and chances of experiencing more lightning events over a period of time over the life of the application is certainly higher in these particular regions. And there are industry organizations like IEEE, especially, that have done studies in the effects of outdoor equipment due to lightning type of events. And they have produced guidelines or recommendations on how to evaluate end equipment based on the studies that they've done. And then other standards, as you'll see, have kind of pulled from the IEEE standard to develop their requirements for mitigation against surge due to lightning events or other type of switching events. So the most common way of simulating a lightning strike to evaluate end equipment is done with something called a combination wave generator. And what this is essentially is comprised of an open circuit voltage waveform component and a short circuit current waveform component. That's why they call it a combination wave. And each of those waves are a double exponential waveform. Essentially means that it has a very fast rise time and then an exponential decay. The open circuit voltage waveform is defined as a 1.2 microsecond rise time to peak voltage and a fall to half peak voltage over a 50 microsecond duration. The short circuit current waveform is defined as an 8 microsecond rise time to the current peak, and then a fall to half peak over a 20 microsecond duration. So you'll hear me refer to, and you'll probably hear this in the industry fairly often when people talk about 1.2 by 50 or 8 by 20. This is really what they're referring to. They're referring to kind of a standard lightning wave shape that's used to evaluate equipment for lightning events. And then how we protect against this is we would use a suppression device, for instance, like a metal oxide varistor. And essentially what that does is that clamps off that peak voltage level and reduces the amount of voltage that actually ends up getting dissipated or propagated into the end equipment. And that's how we suppress against these type of events. The chart in this particular slide is taken directly out of the IEEE standard, which is IEEE C62. And based on their studies, what they've done is developed, again, recommendations for how to evaluate or test levels that they recommend to test end equipment to. And this is based on the location of the equipment within the electrical system. So for instance, if this is at some distance within a facility down the line of the electrical system, then it's a much lower level of energy or level of surge that they recommend that you test to. If it's closer to the service entrance or near the distribution panel, then there's a little higher level. And then for outdoor equipment, they have both C-low and C-high. C-low is geared more towards outdoor structures like parking garages, whereas C-high is geared more towards high level of exposure of outdoor equipment, such as a lighting fixture. And these tests are applied in a couple of different modes. The first one is a common mode test in which they apply the surge to both line and neutral, or line 1 and line 2, depending upon the system, in relation to ground. And then the other is a differential mode where they will apply the surge to line in relation to neutral or in relation to the other line on the system, depending on the system configuration. And what's shown here are the most common standards that are referenced when it comes to lighting equipment. The Department of Energy was really the first ones to make an attempt at trying to standardize how to evaluate or how to test lighting fixtures or LED fixtures for lightning and switching immunity. And this was used by a lot of municipalities when trying to determine the levels of requirements or what their test requirements might be given a particular installation. IEEE C62, which is the one I've talked about quite a bit already, essentially provides recommendations on evaluating equipment, low voltage AC equipment, which essentially means anything under 1,000 volts, low voltage AC equipment to transient threats. And this could be either switching surges, lightning surges, or so on. And IEEE is really the base standard for which most other standards for equipment or equipment standards will pull from when developing their standards and how to test for lightning immunity or transient immunity. And one of those would be the ANSI 136 standard. And ANSI 136 is specifically geared towards roadway and area lighting equipment or outdoor lighting type of equipment. And it pulled both from the DOE spec as well as the IEEE spec and developed the requirements or needs for testing or evaluating lighting fixtures against transient energies. The next one is ANSI C82. And what C82 did was basically just try to encompass all type of lighting fixtures, where C136 is geared more towards outdoor lighting. C82 is geared more towards any lighting, whether it's indoor, outdoor, or what have you. And for the outdoor portion of the standard, it really pulled directly from C136 as far as its recommendations are concerned. And then a couple other standards, you may or may not be familiar with. UL 1598 is really just a Luminaire standard, and it goes beyond lightning immunity or transients. It's just a holistic standard for luminaires and being compliant to UL. And then UL 1449 is a surge protection device standard. And this really becomes kind of important or key as we get farther into the presentation and talk about surge modules and those types of devices that are used to help protect outdoor lighting fixtures. So a little bit more detail on C136. C136 does have a couple of different test requirements to it. There's a test requirement for a ring wave. There's also a test requirement for electrically fast transients. And then of course, electrical tests for lightning. I'm gonna focus on the lightning because kind of as I had mentioned before, if you comply to the lightning requirement of this standard, more than likely you're going to be able to comply with the other two, ring wave and EFT standards, which are geared more towards line switching or load switching on the grid, whereas this is geared more towards lightning strikes. But if you comply with this, you'll typically be able to meet the other aspects of the C136 standard. And the C136 lightning specification breaks it down into 3 different levels. There's a typical level, an enhanced level, and extreme level. And that's really based on the installation where the lighting is going to be placed. For typical level really applies to more kind of building attached or building entrance wall wart type of applications where it's actually connected to the electrical system within a facility or within a building. And that's a much lower level, so a lower level of exposure of only 6 kV, 3 Ka. Enhanced level applies to more outdoor structures such as a parking garage, a tunnel, or maybe even a parking lot. And that is a level of 10 kV, 5 Ka. And then the extreme level is more for roadway lighting, stadiums, airports, anything that is really purely outdoors, high level of exposure. And that test level is 20 kV and 10 Ka. And these are really the minimum levels in order to be able to comply with the C136 standard for lighting.
Hey Mark, if these are the minimum standards, then what's the benefit of going to a 40 kV, 20 Ka surge suppression system?
So generally speaking, and I'll talk a little bit about this, there's a pulse cycle capability to suppression devices, meaning that after they are surged a number of times, they will eventually degrade and potentially wear out. The higher that you rate a suppression component or a suppression device, the more reliability you're going to get at, say, lower surge current levels. So for example, and it really increases almost exponentially as you go down. So, you know, for a, say for a 40 kV device, it will survive, you know, 10, 15, 20 pulses at 10 kV. It'll survive maybe 100 pulses at 1,000. But if you're at a 10 kV device or a you know, a 6 kV device, you're going to be a fraction of that as far as reliability is concerned. So the real key to using a higher rated type of device is you increase the life or the reliability or pulse cycle capability of the device that you're using to protect your fixture.
Thanks, Mark.
The other thing I'll point out here real quick is this also kind of describes the different coupling modes, common mode, differential mode, what phase angles you need to surge at, as well as the number of strikes and intervals for each of these. And it really ends up breaking down to the fixture itself would end up having to be able to withstand a total of 40 strikes when you start combining all of the different phase angles and coupling modes that need to be tested. So it's a pretty high level. All right, so we'll talk about some of the components, how they operate, what they do, and we'll compare and contrast some of the technologies. And then I also want to talk a little bit about thermal protection and the importance of that particular feature of suppression devices. So this is really a very basic diagram. So you have the power source on the left, and what's not shown on the right would be the load. And you have a suppression device or an overvoltage suppressor, and those are placed across the line or in parallel to the source and the load. Under normal operation, they're going to be a very high resistance, and current will flow from the source to the load and then back to the source. But under a transient event, the suppression device is going to change its resistance value to a lower resistance and begin to conduct a higher level of current, and therefore dissipate or redirect the energy away from the load. So under a lightning strike, you'll see that it gets redirected through the suppressor, and some of that energy is dissipated within the suppressor, so it heats up. So it's kind of thermally cycled as the energy is dissipated within it. But that's kind of the basis of how a suppression device works. There's two different types of suppression devices used in the industry. The first one is a clamping device, and a clamping device essentially will lower the peak voltage let through to the end equipment during a transient event, and it will clamp it down to a level that's above the operating voltage of the system, but below or ideally below the damage threshold of the equipment being protected. And then once the transient dissipates, it will go back down to operating voltage and go back to normal operation. Examples of this are metal oxide varistors and transient voltage suppressors, or TVSs. Another type of device is called a crowbarring device. And a crowbarring device has an operation that when a trigger voltage is reached due to a transient event, the voltage actually drops down to a very low voltage level, near zero, usually in the range of anywhere from about 5 to maybe 30 volts, depending on the device, and will conduct current until the transient is dissipated, and then it will delatch and go back to normal operation. In power applications, a crowbarring device is typically not used. The reason being is once the transient dissipates, if there is enough follow-on current or follow-on energy after the transient, it will keep the crowbar device in the latched state until it will eventually burn up. So it's not really a good operation for this type of device. Because of that, they're typically not used in power applications, especially AC mains or DC power circuits. They're used more for primary protection or protection of telecom circuits, which are more high impedance lines. So it limits the amount of follow-on current that would be seen by the device. So metal oxide varistor is essentially a ceramic-based technology. It is inherently bidirectional. It's a clamping device, and it provides, its really key benefit is it provides very high surge handling capability. You can get up to 10,000 amps in a 20 millimeter size component. And it's relatively cost effective as well. So it does allow for very high transient energy capability. A couple of the drawbacks is it does have a little higher let through voltage, or it doesn't clamp as low as some other types of devices. And it also has a limited pulse life, which we kind of talked about a little bit, that Now, it will handle so many pulses over its life until eventually it may begin to degrade and wear out. Transient voltage suppressors, on the other hand, are also clamping devices, but they have actually a faster response than a metal oxide varistor, and they clamp at a much lower level, all things equal, than a metal oxide varistor, and they also have an excellent pulse life. So you can actually surge them as many times as needed. As long as you don't exceed the peak ratings of the device, it will not wear out over multiple pulses. The disadvantage of a TVS diode is that it has minimal let-through power, or has minimal surge capability. So it's really only a fraction of what a metal oxide varistor can handle. So generally, you will not see these devices used on AC mains just because they don't have the power capability. There are some exceptions, but those exceptions do come at a cost premium. And then finally, gas discharge tubes. Gas discharge tubes are fairly slow reacting. It does take a while before they will begin to clamp, so they have a fairly high let-through voltage compared to the other devices before they actually trigger and go to a low voltage value. However, they do have the advantage that they have extremely low leakage. It's essentially an air gap, so it's going to have much lower leakage than either a TVS diode or a metal oxide varistor. But of course, there's also the issue of follow-on current. But one way that GDTs can be used on an AC main application is in conjunction with a clamping suppression device like a metal oxide varistor. And what it does here is there are some situations where you may not be able or allowed to connect a metal oxide varistor to ground. Because the leakage current is higher in a metal oxide varistor, they don't always allow that to be connected to the chassis or to ground because there's a potential for a shock hazard. So what is done in some cases, that actually a GDT is used in series with the metal oxide varistor and connected to ground. Because of its low leakage, then there's no leakage onto the ground line, so you don't have the risk of the shock hazard under normal operation. And then under a transient event, the GDT will trigger, begin to conduct, as well as the MOV will begin to clamp. And then once the transient dissipates, there's enough resistance in the MOV that it will choke off the follow-on current, shutting off the GDT and allowing everything to go back to normal operation. Another aspect of protection is thermal protection. And there's a couple of reasons why this may be necessary. The first is if the system ends up in an overvoltage condition or what they call a double overvoltage condition, the MOV will turn on and begin to conduct. An example of this might be if you're using a split phase 240 system and you lose neutral. Now instead of 120, you've got 240 across the MOV. And if it's in line with a high impedance load, it will actually limit the current to a point that it may not open the fuse or trigger a breaker, but the MOV is still going to sit there and conduct continuously, which it is not designed to do. Another condition can be once the MOV reaches end of life, it starts to conduct more current or becomes more leaky. It starts to heat up and begins to conduct even more current, and then eventually ends up what's called a thermal runaway condition. So what the thermal element does is we integrate it into the package of the MOV. So when that MOV begins to heat up, either due to an abnormal overvoltage condition or due to an end-of-life condition, it will actually disconnect it from the circuit or from the line, preventing it from going into a thermal runaway condition. And I have a short video here to kind of show you or to demonstrate that. What I have here is Mod 1 and Mod 2 are MOVs that don't have any thermal protection, and we're going to apply an abnormal overvoltage limited current test to them. And then the last MOV is a thermally protected MOV, and we're going to apply the same test to that, and you'll kind of see what the effect is of these components. Now, if you pay attention to the thermally protected device, you'll see a flash that occurs, and that's essentially the thermal element activating and disconnecting it from the circuit. So therefore, no more current is now flowing through that device. There's a little bit of discoloration, but you obviously don't have the situation that you see with the other two standard MOV devices. Now, you can try to mitigate this effect by having a rugged enclosure or backfilling, those types of things, but those are more expensive and messier type of processes than just integrating a thermal protection element. Okay, so now we'll get into specifics of outdoor lighting protection. The diagram I have shown here is essentially a basic diagram for a LED fixture. So you've got your LED driver, you have your light board on the right-hand side, and there's obviously a lot of protection that could be used throughout the system. But I want to focus primarily on the AC input. So driver manufacturers will integrate a level of protection into their drivers. However, this protection is usually fairly limited. It can range anywhere from about 2 kV to maybe 6 kV of protection. And the reason they do that is because most drivers, it could be used in an indoor application, could be used in an outdoor application. And by integrating a higher level of protection up front, it's over designing and is not really needed for an indoor application. So they're really only designed up to about 6 kV of protection in most cases. So this is not sufficient to place in an outdoor fixture, especially on a roadway or something like that, or even in a structure, because it will not provide sufficient protection. So in order to add additional protection, generally what is done is there's a protection module that is added to the front end of the driver or the input side of the driver. And this module has a much higher surge capability than what is internal to the driver. So most of the energy then will get conducted through the module and limit the amount of energy that has to be conducted or dissipated by the protection scheme inside of the driver itself. So this is really a pretty common practice, and it's very important that this is added when you're applying these drivers in an outdoor application. And there's a few different configurations when it comes to protection modules. You can either do no protection and just hope that the driver protection is going to be sufficient, but typically that's not going to be the case in an outdoor application. Or you can use what's called a parallel connected surge protection device or surge protection module. And this is basically what it says. It's connected in parallel to the line. So under normal operation, it's just going to be in a high resistive state and allow power to flow. Under a transient event, it's going to change its resistance and conduct energy through the module and away from the driver or the light fixture and allow for protection of that device. And the most common components that are generally used in surge protection modules is going to be metal oxide resistors. Now, another option is a parallel connected, thermally protected module. So again, parallel connection is really the same thing, but what we've done at this point is then integrated thermal protection into the element or into the module itself. So if it does experience an end-of-life condition, or if it experiences a abnormal overvoltage condition, the thermal element will activate, disconnecting the module from the circuit and preventing it from going into that type of kind of catastrophic type of failure. The issue with this is once the module is taken offline, you no longer have surge protection. So the next transient that comes down the line, your driver is going to be fully exposed to that. So another option is a series connected surge protection device. And the suppression devices are really still connected in parallel, but the thermal element is now connected in series. So under normal operation, everything will be fine. If you end up in an end of life or over voltage condition and the thermal element activates, it will actually disconnect the driver or the fixture from the AC line. What this does is then isolate it from the AC line, so no more transients can be transmitted down the line to the driver itself. And it also actually ends up shutting off the light, which provides indication that that fixture or that unit needs to be serviced. And my last slide here is really just to provide you with sort of a high-level overview of the type of modules that are offered by Littelfuse. And there's sort of a progression on how we've come through to meet the needs of the lighting industry. The first one, starting on the upper left-hand side, is our LSP10, and then below that is our LSP05. These were kind of our first standard modules that we developed. The LSP10 is a 10 kA module. The LSP05 is a 5 kA module. The LSP10 is available in both series and parallel connected and is thermally protected. The 5 only comes in parallel connected, but is also thermally protected. The next one was the LSP05G. And what we did with this is we integrated a GDT into the product as well to provide that ground isolation under normal operation, as well as provide the thermal protection and surge protection in both series and parallel connections. The LSP05NP, essentially what we did is we took the thermal protection out of the unit to provide more of a lower cost option to the standard LSP05 product. Then the LSP10GI and the LSP05GI are essentially the same as previous as far as surge capability is concerned, but we've added in an LED indicator, or integrated an LED indicator, so that if the thermal element activates for some reason, it provides indication that the module needs to be replaced or needs to be serviced. And then finally, there's our LSP10GIHP, and HP stands for high performance. What we've done with this device is we've added in some additional components that reduce the amount of let-through voltage that is seen by the driver. So it actually provides a much higher level of protection, better level of protection for the application or for the fixture itself. So that comes to the end of my presentation. I hope it was informative. I'll be happy to take any questions that you might have at this point.
Okay, Mark, we got one question that came in from Kenneth, and he's asking, are these designed per unit or per fixture installation? As opposed to, I'm thinking stating as opposed to like for an entire area of fixtures.
Yeah, these would be intended for a per fixture application. So there would be one per fixture on the input at the fixture itself, not system level.
Good question. If you were to, most fixtures come with UL, you know, that they've already been UL 1598 approved. If a fixture manufacturer manufactures this without it in it, can someone safely put one of these inside it on site, and would they be violating the UL 1598 that the fixture already has?
Yeah, that's a good question. I don't believe it violates the 1598 because this is, you know, it's a good question. It shouldn't violate the 1598 approval. Normally, though, what you would do is when you would go in for 1598, you would do the fixture as a whole, as my understanding is. And generally, the module would already be included. If you were to add a module, I would think at the very least, at best, it would be maybe a paper qualification or something like that. That's a good question. I might actually have to reference that to my standards manager and ask that question, and I could get some more detailed feedback on that. But I don't believe that it would affect the certification or qualification to 1598.
So Ken, okay, great. The question that came in, on our street light system, we are using a 2 wires and we are jumping the neutral and the ground at the connection block. Do you see any issue with using an SPD function using a series SPD? Question mark.
No, all you're going to be doing at that point, though, is the suppression between the neutral and the ground becomes null and void. But it would still provide differential mode protection. But it should not affect operation either of the fixture or of the module itself, other than, you know, you're basically bypassing the neutral to ground suppressor within the module.
Kind of along that line, what we're finding in the out in the marketplace is that when there's contractors that are just doing a swap, they're swapping one head, a metal halide or a high pressure sodium complete head for an LED head. And even though there might be a green ground wire sitting there at the top of the head, it doesn't mean that it actually goes anywhere. It could have degraded over time and come loose. It could have been chewed through by a mouse. In many cases, there's a lot of people not actually going into the anthole or below looking to make sure that it's grounded. What happens when the surge suppression unit itself is not actually physically grounded?
Yeah, so it may or may not necessarily be an issue. And the reason being is because the ground protection or common mode, as it's referred to, is really a test of the insulation resistance or insulation capability. And it may depend on how the driver is connected as well. So if the driver is grounded, and you don't have the module grounded, then the driver is exposed in common mode. Now, if it has enough insulation resistance that it can hold up under a high level transient event, then it may not necessarily be an issue. But if the insulation is such that it can cause a dielectric breakover, then you can end up with arcing inside of the driver, or something like that. And a lot of it depends too on whether it's a class 1 or class 2 type of installation. Whereas, and I'm trying to recall here, I think in class 2, generally there is not a ground line available. So in that case, it wouldn't necessarily be an issue. And again, it's just that the common mode protection becomes null and void. And it really is dependent upon the insulation resistance of the fixture or the components within the fixture.
Gotcha. If they're not putting the surge suppression unit into the actual fixture, how far away from the fixture can it be mounted?
That's a good question, and I've had that question before, because there are those that ask, can I place it at the base of the pole, and things like that. You can. But our recommendation is you try to place it as close to the driver as possible. And the reason is, if you place it at the base of the pole, that wiring that runs from the base of the pole to the fixture itself becomes an exposure point for energy, especially a lightning event. It can be coupled onto those lines. And since the module is at the base of the pole, it's not providing as much protection as it could if it's placed in the fixture. It will still provide some protection, and it will provide some protection that comes from, farther upstream in the electrical system. But for optimized protection, we do recommend that you put it in the fixture next to the driver.
Gotcha.
And we also have a follow-up here with Monty's question. He's asking, would there be an advantage to adding a third wire to the pole for earth ground? We bond the neutral to the steel poles at this time, and it would provide another path only. Is that correct?
Yes, you're talking about bonding the neutral wire to the pole?
Yes, we bond the neutral to the steel poles at that time. Okay,
yeah, so that actually, yeah, because that's good proximity to the fixture itself. So that would, then I'm trying to think about this for a second, sorry. So is the question that, would it improve protection, or, I'm sorry, maybe
So I'll reread what he said. He said, would there be an advantage to adding a third wire to the pole for earth ground, bond the neutral to steel pole, and it would just provide another path only?
Yeah, there could be an advantage to that, because the closer that you are able to make the bonding to ground, the better the protection. So it's because if you can reduce the amount of resistance in the ground plane, it actually provides a good conduction for ground for those common mode type of transients. So if you can add a third wire connected to the pole and use that as your ground, that actually is even better than grounding it back at, say, the service panel.
Okay. Is there any other questions before we get to our final question?
Yeah, Looks like I have a follow-up again with mine. It says, are there any issues with leaving old HID lighting arrestor that's sometimes still in the line installed? They're 600 volt. We're converting to 277 volt for LED. Any issues with both the arrestor and SPD in service?
No, it might depend on how old the suppressor is and, what its life expectancy is. But really all you're doing at that point then, if you're using both, you're kind of doubling up. So they'll start to, in some ways, share the transient energy and maybe even provide a better level of protection.
Okay. All right. Well, we're going to get to our final question here. And so if you look in the chat section, you'll see the question. This is kind of like Jeopardy in that the first person to buzz in and answer it is going to win a $50 Amazon gift card. So I know that Amazon gift cards right now is good currency for sure. So let me go ahead and place this in here. First one to answer that gets a gift card. And the winner is Bill Lindsay. The answer is all of the Lumecon fixtures come with a Littelfuse 20 kA 40 kV surge suppression unit. Dang, it's making a lot of noise. So thank you all to everybody. I appreciate you coming in, and please try to stay safe out there. And a special thank you to Mark Hubbard for spending some time with us today and giving us a little bit more knowledge on surge and surge suppression units. Thank you, Mark. Appreciate it.
Thank you, Bob. I appreciate the opportunity.
And Michael, thank you. And everybody else, take care out there and be safe, please.